Welcome back to General Chemistry Mini Lecture Series, Lecture 22, Stoichiometry. We already learned in the past to convert from mass of a substance to the moles of substance using molar mass, or convert from particles to the moles of a given substance using the Avogadro number. And today we are going to concentrate on stoichiometry. So we are going to find out the quantities between two chemicals in a chemical reaction, mainly using the coefficients, converting from moles of A to moles of B. Both could be reactants, both could be product, or one of them can be reactant, the other one can be product. Really doesn't matter. So we will use the coefficients in a balanced chemical reaction to write conversion factors. Stoichiometry is a numerical relationships between chemical amounts in a reaction. For example, in this reaction, gasoline has a very high concentration of octane, and when that burns inside your car engine, it produces CO2 and water. The coefficients in a balanced chemical equation specify the relative amounts in moles of each of the substance involved in the reaction. For example, in this particular reaction, we can say 2 moles of octane with 25 moles of oxygen to form 16 moles of carbon dioxide and 18 moles of water. And you can write down the mole relationships here. The coefficients, as I mentioned a while ago, are used to write conversion factors. Okay, so therefore there are so many conversion factors you can actually write for this chemical reaction, depending on what you need to do. If you need to convert from moles of octane to moles of oxygen, you use this conversion factor. 2 moles of octane is equivalent to 25 moles of oxygen. Or if you want to do the opposite, you want to convert from moles of oxygen to moles of octane, this is the conversion factor you need to use. And so on and so forth. You can write so many depending on what you need to do for a particular question. The mole amounts of any other substance in a chemical reaction can be determined from the mole amounts of just one substance. So remember that. That's the key concept of stoichiometry. Let's work on one example to help you digest the subject matter here. How much CO2 can be made from 22 moles of octane in the combustion of octane? It's a chemical reaction, and it is a balanced equation, so we can use those coefficients in stoichiometry. So we start from what we know. We have 22 moles of octane. We are converting from moles of octane to moles of CO2, and then use the coefficients, right, in this balanced chemical equation to come up with this conversion factor. Then after that, you see, we have 176 moles of CO2. That's example 1. Now example 2, how much oxygen is needed to completely react with the 22 moles of octane in the combustion of octane. Again, the same chemical reaction, but now we'll work on 2 different substances. This time it's between oxygen and octane. So we will just use the relationship between octane and oxygen. We start from what we know. We know 22 moles of octane. Again, we are converting from octane, moles of octane to moles of oxygen. So you use the coefficient from the balanced chemical equation to come up with this conversion factor. That's 275 moles of oxygen, which means you need 275 moles of oxygen to completely react with 22 moles of octane. In this example, we are going to convert the mass of one substance to the mass of another substance. So it's not only just one-step dimensional analysis that would require, this one will require 3 steps. Okay, it's the same chemical reaction. And since so here it involves CO2 and octane, so we just write down the relationship between these two. 2 moles of octane yields 16 moles of CO2. Okay, we'll start from what is given, 5.35 kilograms of octane. First, we need to convert that from grams to moles of octane, so that those are grams are cancelled. Okay, now we can apply stoichiometry, converting from moles of octane to moles of carbon dioxide using the coefficient in the balance equation. So now moles of octane, they are cancelled. What you have on top is really just moles of CO2. But what is asked? It's not the moles of CO2, it's the mass of CO2. So therefore, we need to convert from moles of CO2 to the mass of CO2 in grams. And now we have the answer in grams for CO2. Let's work on the limiting and excess reactant. For chemical reactions, it is most likely that one of the reactants will be depleted before the others. That always happens. And when this reactant is used up, the reaction, of course, will stop and no more products can be made. Let's take a look at this example. 2 hydrogen molecules reacting with 1 oxygen molecule forming 2 water molecules. Okay, so that's another way of representing this reaction. And now, if we start with 4 oxygen molecules and 4 hydrogen molecules, then after the reaction, how many water molecules are formed? That should be 4 water molecules are formed. Therefore, before the reaction, we have 4 hydrogen molecules, 4 oxygen molecules. After the reaction, we have 4 water molecules, but still have 2 unreacted oxygen molecules. If you count the total number of hydrogen atoms before the reaction, 8. After the reaction, 8. Oxygen atoms before the reaction, 8. After the reaction, 4 here and 4 here. Okay, now you see which one is used up. In this case, hydrogen is used up. So therefore, hydrogen is a limiting reactant. And what still do you have left over? Oxygen. Okay, so therefore, the limiting reactant is hydrogen. And then the excess reactant is oxygen. That's how you understand the limiting and excess reactant. Theoretical yield is basically the amount of product that can be made from the limiting reactant, because after the limiting reactant is used up, reaction stops. No more products can be made. The actual yield is actually the actual quantity obtained after a given reaction. Typically, it's always lower than the theoretical yield. And then the percent yield can be calculated using this equation. That's the 3 different yields we describe a chemical reaction. How to find the limiting reactant, theoretical yield, and percent yield? Of course, there are guidelines. Number 1, we need to convert the mass or mole amount of each reactant to the mole amount of the desired product. I'm going to use one example. So right here, we have acetic acid as the product, okay? And we have 96.12 grams of methanol and reacting with 56.02 grams of carbon monoxide. You see the quantity of both reactants are given, but we want to convert the mass of those reactants to the moles of the desired product. Desired product in this reaction is acetic acid. So, and we have two reactants. So let's work on that. First, 96.12 grams of methanol. We are converting from grams of methanol to moles of methanol. Grams of methanol and grams of methanol. That's cancelled. And now we have moles of methanol on top. Now we are going to carry out the stoichiometry using the coefficient in the balance equation, converting from moles of methanol to the mole amount of the desired product. In this problem, the desired product is acetic acid. So therefore, moles of methanol, that's cancelled. We have mole of acetic acid. So we converted from grams of methanol to moles of acetic acid. We need to do the same for carbon monoxide. 56 grams of carbon monoxide, converting from grams to moles of carbon monoxide using the molar mass. And now the second one, converting from moles of carbon monoxide to the moles of the desired product. The same product has to be acetic acid, just like here. Okay, now it's 2 moles of acetic acid. Guideline number 2. The reactant that yields the lowest mole amount of the desired product is the limiting reactant. Okay, which number of these two is lower? Of course, this one. And then the reactant that produces this number, that's a limiting reactant. So therefore, carbon monoxide is the limiting reactant. Next, how do we find out the theoretical yield? The mass of the product calculated using the amount of the limiting reactant is the theoretical yield. So therefore, we already know from this reaction here, 2 moles of acetic acid, we are converting from moles of acetic acid to grams of acetic acid. So therefore, 120.1 grams of acetic acid is the theoretical yield. Percent yield can be calculated using the actual yield divided by the theoretical yield times 100. All right? So we use this key equation here. And what is the actual yield that should be given in the problem? In this case, is 72.06 grams divided by the theoretical yield we just calculated from this step times 100. That's 60%. Here are the first 2 end of lecture 22 quiz questions. Let me start with number 2. So number 2 is continued from question number 1. In question number 1, it asks you to write down a chemical reaction of ammonia with oxygen forming nitrogen and water. So this is the balance equation. Therefore, the answer for question 1 should be D. Let's take a look at question number 2. Based on the balance equation in question number 1, which is also here, how many grams of ammonia it takes to make 108.1 grams of water? Okay, so we are going to use this calculation strategy here. So we know grams of water. We start from grams of water. Then we convert that to moles of water. And then from moles of water to moles of ammonia. And then from moles of ammonia to mass of ammonia. So that's what we are going to do. And we will do exactly that. Start with what we know, 108.1 grams of water, converting from grams of water, they are cancelled, to moles of water. That's this step. Next step, converting from moles of water to moles of ammonia using the coefficients in the balance equation. Moles of water, they are cancelled. Now we just have moles of ammonia. And we can use the molar mass of ammonia to convert from moles of ammonia, moles of ammonia, moles of ammonia, they are cancelled. And now we should have grams of ammonia as the unit for the answer after taking care of the sig figs. D should be the correct answer. And you can keep working on additional quiz questions. I will see you guys in lecture 23.